All right, so now we are taping.
We cannot hear you, Samson.
Oh, you can't hear?
Yeah, now we can.
Can you hear okay now?
Yeah, now.
Okay. I think I had my hand on the computer. Okay, so let me start sharing screen. I was able to bring down some data, some EX LoopI data from as ISO, and I convert to save file, and I hope I can open up now. So let's see what we can do. Uh, okay, so let me read one star 313. So restore star 313 dot save, and let's call W low is equal W and S low is equal S. So if I plot W low, S low, I should get a graphic here. Put you guys down here. Oh, okay. I think I need a bigger screen, huh?
Yep.
Okay. So that's, oh, this is crazy spectra, my goodness. Okay, so let's find the high resolution, and I think it is, it's right there. So CD tutorial EX dash LoopI. And then let's restore one of these data here. So restore star 10, 10.7. Okay, so now we have, let's call W high is equal W and S high is equal S. So far, you guys know what I'm doing, right? Because I saved this data, the low resolution and high resolution in these .save files, and I call wavelength and flux or data W and S. I should have saved them with a different name, but I always use W and S for some reason. So I have to differentiate them. Otherwise, when I restore, it's gonna erase, it's gonna copy over the previous variable. So if I plot now W high and S high, then it's gonna be, so that's what I got. Let me do something different because let's say this is the high resolution data, but the scale is all crazy, as you can see. This wing over here is just junk. So if I do plot this data divided by, let's say, putting a range that is 4,500 and 5,000, because I know the low resolution data goes in there. Now I can see a little bit better my data, but I still can't see well, so let me take this and divide it by the mean of S high. So I'm taking the high resolution divided by some number that is equivalent in value, so that maybe I can see it better. I still can't see it. There's lots of emission here, or maybe this is a spike. Let me limit the axis to 0 and 2 in Y. Okay, now I can see something better. There is lots of stuff, and I think it's better.
That was normalizing when you were dividing it by the mean.
Yeah, I'm trying to normalize so I can try to compare the two spectra, so we can have a sense of what does it mean to be low resolution and what does it mean to be high resolution. How can we compare pretty much profile, and what sort of information can we derive if we work with low resolution data or with high resolution data. So high resolution implies we are having access to much more information, because we can see not just few lines, as Philip maybe remember seeing in the low resolution data, but here we can see millions of lines. And then we can do much more science with high resolution data.
How much from this data is noise from the measurement?
That's a good question. So to know that, let's reduce the spectral window. Let's go, for instance, from 5,000 5,000 and let's take only 50 angstrom. 4,650. Oh, too many zeros. Okay. Now we can see something better. Although I don't know what these lines are, I could do a little bit of cleaning up. And now what I would do is to bring some of these routines that is in the library that you have access. One of these routines called smooth. And what you do, you call your spectra, and you say, I want a smooth, which means take an average of the value in pixels every 5 pixels, let's say.
So this is kind of sliding window.
Is a kind of what?
Sliding window.
So right now, that's what I reduced the window to 50 angstrom, but I'm gonna try to take a little bit of the noise, as you said. So I gave a little bit of a cleaning up, and I can do it more, but if you do too much, we ended up losing information. So now I'm taking 10 pixels and I breaking down. So it seems to be to the point we can see some lines, some features in here. And I could extend that 6,600, 6,000, let's say.
So we are deciding how to do the filter.
Yeah. This is the type of thing that when we start working with data, we make this decision. Say, oh, I don't like the way the data look. I think it's too noisy. And then you go to your logbook, see if there was any problem with the data process, and then you get to some conclusion. I could later on, as we advance, I could do what's called normalization. I could take polynomial and pass the polynomial through these lines just so that I can normalize everything and then have different spectras normalized to the same level, and then I can compare them better. For instance, let me see if I can pull up a line.
To translate it to the language of electrical engineering, that is signal processing, cleaning, wall, pass filters.
There you go. There you go. 65, 65. 4, 8. Let me see H beta. 8.
Excuse me, one more question. When we do mean of S high, it is taking the array, all measurements of S high, and it is finding the median. This is how.
Yes, this function mean automatically find the mean in the whole spectra, the whole range that you are considering, and then divide by the mean. There is another one that is a median that does the same process. So let's say I want to compare this spectra. This is an H beta, is an hydrogen line. So 4,500, 600, 700, 800, between 5,800 and 5,000. So if I plot this in the range 4,000 and 6, 7, 800 and 5,000, right? So I'm gonna plot in that range, and I'm gonna divide also by the mean. And I did some silly mistakes.
I think you have to do 5,000.
5,000 it is, and I forgot to put a equal. All right. So now I have my spectrum more or less normalized here, right? Around 1, and I have H beta, and I have some other line. I don't know what it is, but it's interesting that has this P Cygni. It's called P Cygni, like Cygnus, the constellation Cygnus. There is a star, is a P star, P Cygni. That was the first one they found this type of profile that have a shoulder that goes in absorption, and for that particular star, the shoulder in absorption was in the other side, which indicates the gas is expanding. So in this type of star we are studying, the gas is not expanding, but it's falling on it, and this shoulder here indicates that. So I haven't seen this before compared with high resolution, and that's what I will try to do now. I will plot this graphic, but I'm gonna put an ampersand saying that I will introduce another command, and I will overplot the high resolution data. S high divided by mean S high. See if I can pull this graphic in there. Is this correct?
So you mentioned the shoulder. That means that it is expanding. Oh, okay.
Okay. Now they are kind of appear in the same window. So let's say I forgot to do the smooth thing. So I'm gonna do a little smooth in there, and I think 10 pixels was good. See if I improve. Now I can see something better going on. I think I can.
Okay, so this is unfiltered. This is.
Yeah, I put a filter, so I reduce a little bit of noise. Oh, I haven't defined colors yet. Oh, I have to define my palette. Sorry. So it's right there. So, but I think I have to. Probably would be better if I divided this by 0.4. Since I wanna give a quick look, so I divide whatever I have there by 0.4, so I can bring them quite almost together, right?
then you see what kind of information was lost by the filtering.
There you go. Exactly. So I can even go to the previews and extend a little bit the y-axis. And
the shooter, what we have seen, that can be seen just only after filtering, or because from the raw data it is a little bit difficult to see the shooter.
yeah, let me see if I can improve the visualization here. 0 to 4. Not enough. Would be nice to have a color, and I will put more filter here, probably 15. Now we can see with a little bit more of details. So the two specters are there. The low resolution is almost aligned. You don't have the details that appear in the high resolution. Um, in this particular observation, if I move a little bit up, in fact, you can see the profile, the H beta profile is kind of extended. It's kind of a bigger in there.
Yeah, so is this based on the raw signal, or is it a physical phenomenon that the extended H beta?
This is the star itself. Is the star who produced it. This region here is too blue, and the signal to noise is not that great in the blue. We could. I don't have. That's low, high resolution. So I don't have um, uh, data in the red part of the spectra, where, for instance, H alpha. We all know about H alpha located, but I could pull up H alpha here, 6,500, 6,700.
Oh, I see. Okay, yeah, you're putting here H alpha. That was H beta.
Yeah, that other one was H beta. Now I'm gonna put H alpha, but I don't have H alpha. Uh, I don't have H alpha in the low resolution data. This is the high resolution data, and this is pretty much H beta. So it seems to be smooth. It's very intense, but it's nicely symmetric. There is a interesting lines. 5,800 is a helium line. That's the one over here, and then we can do science with it too. So and you have these two lines over here that show some inverse preceding. So all these little thing, we have to get used and see what type of science we want to do. And for now, especially for the students, Philip and Shaunak, Pranati, I don't know if she'll have time to work with us, but she's curious in knowing what we want to do. Um, I would like to get probably take some time and discuss some of the science that was done with this data before and get you guys used to manipulate the data basically. And as you start manipulating the data yourself, you are going to learn the program, how to use this language and create your own program. And perhaps when we are ready to because I have a lot of data that I publish, but most of the data I have it was not published. And then I think one thing simple we could do is just to make the data available online. So in our website, the EVC CSI website that I have to start creating one, we could open boxes with the work the students will do and just make it public. So it's there instead of staying dead in our machines, we can make it probably useful for whoever is doing research.
So that means the idea is part of the data to be the students to process the data, high resolution data, so that everyone can access, for example, what you have shown right now. I mean, to go to the different bands and
yeah. Well, that would be good. I mean, when I think I sent Philip some couple of papers we did with some of the low resolution data. There was a lot of technicality in there, lots of investment and time. We don't have none of that right now. But
just give me a sec to see whether he has some kind of technical difficulties. I see he's not. He's.
No, I'm here. I just didn't have the video on.
Okay.
Okay. But Philip, you were able to pretty much play around with data, right?
With Philip, we went today. We were going through the paper. Philip, you can say a few words.
Yeah, we went through like the first half, and we were looking at how you can analyze the periods by looking at the veiling of the star.
Yes.
Yeah, so we were just.
Oh, so then you went very much far. Okay, when we do analyze veiling, I mean, you have all these stars that are undergoing all kind of changes, and these changes are, in fact, translated in features in either in the absorption lines or in the emission lines. And then your job is pretty much like a detective, is to figure out if there is a shoulder in the line, what that could be. Is that an expanding gas, or is the gas that is falling? And if it is what you think it is, can you see the same feature in other lines that are not so much sensitive to the environment the line you were looking before is? So we have lines that are probably formed pretty much far away from stars. We have lines that are formed in the star. So then you can do this type of analysis. But the basic thing we do, the starting point is, okay, I have a crazy star, and here I have the spectra of a very quiet star, and we call those quiet stars templates. So what you do, you take, ideally, let's say with high resolution data, you take your high resolution data of your crazy star, of your wild star, and then you compare that with the low resolution data or high resolution data of a quiet star that was taken with the same instrument. That's the idea. So when we advance to the point of start playing with the high resolution data, FAIRs, we have to read out which resolution the data has. Let's say is 50,000 resolution, let's say if that's the case. And then we have to ideally look for quiet stars observed with FAIRs that are available and made it online. And then we can download that data, and then we can measure veiling, for instance, which is how much some of these absorption lines happen to be filled up by some external emission that is probably produced in the interface between the disk and the star. So it's a beginning point. So right now we are just okay. I think I understand what's going on. I know what type of program I can use. So we measure the veiling in the case of low resolution data with a series of spectrophotometric standards from Jacobi. And I was today in the morning trying to recuperate this low resolution data online, and I didn't download yet. But it's not going to be difficult to get a set of spectrophotometric standards that we can use to compare our low resolution data in new ISO. And then we can probably publish the veiling of these stars during the time we observe, how the veiling affects H alpha, or in case H beta. We don't have H alpha in the low resolution data. And one extra work that I did in those papers was to model this region using a program named Cloudy. I don't have access to that program, but I'm pretty sure it's online, and it's a matter to download and try to play with it again. So again, we have some road to go, but for now, it's just having fun.
Excuse me, one question regarding low and high resolution data. Does it low resolution? That means we don't have the high frequency bands, or it is about a resolution, for example, pixels per band. So because you
the
were
number
mentioning
the number of pixels that are resolving spectral information.
Okay.
So you have a high frequencies that so the frequencies is higher, which means you can read out more information per frequency window, if you will.
Oh, I see. That means if it is low resolution, because H alpha is very high frequency, that means over there we don't have enough pixel to capture the spectrum. Okay, I get it.
So if you go when compared to what we did before, let's take a look here. So see the low resolution is the one going on top, right?
Yes.
So you basically can't see any absorption line there in this line here. You can't see anything. See this triple line over here? 1, 2, 3. In the high resolution, you can resolve them. In the low resolution, is a big blend.
I see.
Yes.
I see.
It's like TV.
Low pass filter, yeah.
Yeah. So you have the technical skills for that, and so if you take this high resolution data and make a convolution with a function that can mimic the filter and the spectrograph of your instrument, you could downgrade the high resolution data. You could downgrade to the low resolution data and compare both. This is something you can do. If you convolute this high resolution data here, you might be able to blend these lines into what you see in the low resolution, like just one continuum thing. But you lose information when you do that, right?
Of course.
Yeah.
Of course.
Yeah. So the idea,
I just meant, so the other question of the high and low resolution data, it depends on the instrument, because you mentioned that the high resolution data was recording using the ferrous spectrum, right?
Yes. Yeah. So and that, so let me take another star, so we can compare, for instance, different high resolution data. Restore star 10. Let me take another one here, star 26. That's another EX Lupi high resolution data, and then it charge again. See, there are different pixels here. You see that?
Mm-hmm.
A little bit different.
Okay, that means the number of pixels. Also.
Yeah, the data reduction they did, they lost something. So I don't know. So I will call this W high 1 and S high 1 is equal S.
Oh, I see. So W and S, they're automatically loaded and assigned.
There you go.
Restore.
Yes.
So then we get W and S, and you just assign to a temporary variable.
Yes. So when I call, if you are doing programming later on, the students, they're gonna create a program. They're gonna read all this data and do things. So they have to remember this data in the save for SAV format. I save it so that the spectra is always called W. So if they keep reading, it's gonna be recording the information on the new wavelengths in the old wavelengths, and you are losing information. So you have to rename the variables every time you read it. So like I did now, and then we can plot.
So each SAV file already comes with a like a W and an S?
Yes, because I saved it that way.
Okay.
In fact, what I did, I download this high resolution data from ISO. They are here, and I just use an ideal routine. In fact, ISO gives that to you. They gave a prescription, which I think the name of the routine is MR fits, I think, and I just and I just read this file, and in fact I bypassed the header and I saved in this format, and then I was going to create a catalog so I can catalog all that information with when they were observed, what data, and I think I can show you if I can open here.
So, because that was one problem, what I was trying to say to solve from the fits file to get a SAV file, and I couldn't come up with a good solution.
No, you can't. So now I'm gonna overplot. So I'm gonna call and I will overplot W high 1, S high 1, and I will divide by the mean of S high 1. Oh, it did. Yeah, so it's there, but it's funny. It has this little that gives some smooth. Oops. Do some cleaning up. So I don't know what this looks like. Molecular band, I think, but I'm not sure what it is. But as you can see, my IDL is not set yet to overplot with colors, which would be nice to have different colors, and then we can compare data.
It's still understandable. I mean, so when we look at the colors, would be nice.
This is all work we gotta do, right?
Yeah, this is awesome. Thank you so much for sharing that with us. I mean, that makes things much easier.
See, that's the 2H alpha, and yeah.
You mean the big spike is the H alpha?
Yeah, this is the H alpha right here. Let's see. 6560 65 40 65 65 80. So 40 angstrom. There you go. So look at this. So there is a shoulder here. There was not before, but the emission is less. This is junk. This thing here is junk. But you can see the lines are still there. The other thing that we have to take care, so you see the correspondent lines. When we compare any data, you have to make sure the radial velocity is the same. So you are centralizing your line in the rest frame of you, observer. But when we are doing observation, Earth is rotating, Earth is going around the sun and the solar system move in respect to the star, and the star itself has its own motion. So,
excuse me for the interruption. This is the observation of the same star?
That's the same star. Yeah, those are. Yeah,
okay.
Yeah, this is EX Lupi. I download a bunch of EX Lupi.
So that's how you figured out that this outlier over there is junk.
Because see, it's not a smooth transition.
I see.
It's very sharp. This looks like a bad pixel or some junk. Or probably the order was cutting right there, because in a shell spectrograph, the orders are cut and they are taken to the top of the previous order, and then you ended up with edges that are not well fit. And then when they do data reduction, the pipeline take this order and they join together. And sometimes you have some weird junction. You don't know what it is. It's because they are joining the orders in some weird way. So you have
Alert
to be
from
careful.
system UI server. Low battery.
Cable. My computer is
Alert
always
from low battery.
No oxygen. Thank you for your patience, because we are asking a little bit beginners questions.
Oh no, that's a pleasure.
Okay, you brought new bottle of oxygen, right?
I'm sorry, say it again.
You brought a new bottle of oxygen.
Yeah. Oh, in oxygen has a very important transition line. If you are talking about oxygen, 6,300. I'm curious to see how it is. This is a spike one.
Excuse me, would you mind explain once again how the shoulder comes from? Because the gas is expanding. Is it Doppler shift based or something else? The shoulder.
Wait a second. Wait a second. The H alpha is not a spike because of the gas. So you know the solar prominences, right?
Yeah.
The solar prominences have this loop of gas, and sometimes there is eruption, and then the gas comes up and then falls in the prominences, and the gas is pretty much confined there because of magnetic field. So imagine you are looking down on the prominence, right? So if somebody take a spectrograph and point the telescope and the slit to the prominence, it's going to detect H alpha, because prominence is primarily shining in H alpha emission. So the observer will see a gas that rises up, so which means has a blue shift, and then the gas is gonna fall down, red shift. So they observe that. Now imagine you don't have just a prominence, but you have a blob of gas coming out of the disk and just fall on the star. Not only that, imagine that you have your line of sight is in that direction in which the gas flow. So what you see, you are detecting this emission, each photon that is associated with the gas that is following. Each H alpha photon is being redshifted in some funny way.
I see. If it is falling down, it is redshifted.
That's correct. That's correct.
Because the velocity is in the opposite direction as you're observing it, right?
Yeah, there you go. Yes, exactly. As opposed to if the star is expanding, or if the disk and the magnetic field of the star interacts in such a way that you have ejection instead of falling down or accretion. So if you have ejection, and if you are observing this gas coming out, you see features associated with blue shifted gas, because the gas is moving towards the observer.
I see.
Now, to make matters a little bit more exciting, so think that you have this funnel of gas either falling or getting out of the star, and the star rotates. So then you see this flash like a beam of light, kind of going in and out of your view. And then you should be able, if you have consecutive observations, you should be able to see features associated with blue shift or red shift coming in and out of view because of the star rotation. The star.
Okay, that means if we have observations, let's say if the rotation of the star is 5 days,
yes,
that means this shoulder, what we were talking about, it is going to be on the left side, and then it's going to be on the right side of the.
Yeah, it's so. If the gas fall, so let me see if I can get a. Oh, I don't have my pad here. Now I need a whiteboard. Should have a whiteboard. Yes. Oh, you can hear?
Yeah, we're losing you're kind of muted.
Can you hear now? Can you hear now?
No. If you can talk closer to the phone, it will be better.
Oh, I think I have to. I wonder.
Sound, yeah. There it is. Yeah, it was low.
Oh, okay.
Can you hear now? Is it good?
Yeah.
Much better.
Okay. I don't know why this happened.
Alert from Keynote.
Oh, you be quiet. But these features it change when. So if you have this funnel following in the high latitude in low latitude region, and depending on how you're seeing the star, you might be able to see some of this infalling gas going towards the star, but you might pick in half rotation, you might pick the gas on the bottom also falling towards the star. And then instead of a blue shift or a red shift, you might be able to detect some small shoulder of a blue shift because you see the gas below the disk going through towards the star, kind of going towards the star. So there are different geometries, and perhaps we could take a time and get together if we can before the stargazing or so, and then we just go over some quick geometries and discuss
that would be awesome. I wouldn't mind at all.
Yeah. All right, so pretty much that's it. So I will stop taping now because I would like to talk about the conversation with the dean. She gave a bunch of support, but we have to make some managerial decisions for the future. So I will stop taping now because and